Hey, Scott here, and today I thought I would go through some data analysis on the Quantified Knife Project. So I did all this testing and published a whole bunch of data to the internet to try to measure the performance of the top 21 chef's knives. I thought it would be cool to do kind of a deep, nerdy dive into this. So if you're not a knife geek or you're not a data geek, the rest of this may be very boring, but for everybody else, buckle up. So this is the Quantified Knife Project. We can dive into any one of these knives. This is available for free and public at seattleultrasonics.com. Here's the Shun Classic 8-inch chef's knife, and we've got a bunch of information about the knife. We've got the type of steel, the edge angle that we measured, the advertised hardness, and these food cutting charts are kind of the core, sort of the heart and soul. They are the original source data that I captured and created for this project using JRobot Choppenheimer, the robot arm behind me. It's up here on GitHub. If you go to the Quantified Knife Project and go to data, you can download all the source data as an Excel file. And I've just posted a Power BI analysis file, which is what we're going to spend the rest of our time in today. So let's come over to Power BI. Back in my previous life, when I worked at Microsoft more than 10 years ago, this is the kind of software that I helped develop. So let's sort of orient to the world right now. So the lines you see here are the forces recorded as the robot pushed the Shun Classic knife through the tomato from start to finish. And you see that each of these lines has about the same shape, but they're a little bit different. And that's because every tomato is a little bit different. That's why I did 5 trials of each food. In retrospect, for tomatoes, I maybe could have done 20 trials, but that's a lot of tomatoes. For each one of these trials, the knife pushes in and push until we reach some peak here where it pierces through the skin. And then the amount of force required to complete the cut drops way off, but climbs back up a little bit as you go through kind of the midsection of the tomato. We can see if we switch over for the Shun Classic for potato, it's a different shaped graph, but again, all these lines kind of follow the same pattern. Here for cheese, we're just kind of accumulating until the blade is sort of through the cheese. For carrot, we build up force and then the carrot kind of snaps and then we finish the cut. And for bread, it's also this kind of build. Most of the knives weren't able to slice the bread rolls sort of open from the top. So they were kind of pushing and squeezing until there was some yield. Then the next thing that I did to the data is I took these 5 trials and I averaged them. So the idea was we're doing 5 so that we can kind of get an average tomato out of this. And that's what this graph is. So for every point on here, as we move across the steps that the robot took, we take an average of those 5 lines, and now we've got one line that we can use to represent the average tomato or the average cut for this. Now for tomato, the measure that we're using is peak force. In other words, how high did this part of the curve get until we snap through and then proceeded with the rest of the cut. And the reason I chose that is because I think that's kind of representative of a human tomato cutting experience, how much force built up before you pop through the skin. And then the rest of that force is not what we pay attention to when we think about the sharpness of our knives. For bread, we use the max force. So what was the maximum amount of pressure that had to be applied during the cut? For carrot, same deal, max force. How much did you have to crank down on it before it snaps and you start to make your way through? For cheese, I took average force. Unreasonable people could say that, no, you should measure this a different way or whatever, and that's totally fine, but this is how I did it. And you are fully armed with the data that I provided here to take these measurements in a different way. So if we take a look at tomato, we come in here and we can kind of poke around and see where was the max force. And the biggest number I see is 1825. And lo and behold, if we go back to the Shun cutting data, that's the number we see here. Peak force is 1825. So then we do this for all the knives, and then we line them up by their score on that metric, and that gives us the rankings. Now, the rankings are we take your rank for tomato, and we take your rank for potato and carrot and so on, and we average all of those ranks, and that is your food cutting score. So we can take a look at the Shun Classic, and this visualization here is called a ribbon chart, and it shows us each color as a knife and the positions in this chart as their ranks. Don't pay attention to the thickness of the lines. I can't really control that. But we can see the Shun Classic, which had a food cutting rank blended of 7.2. So it did quite well in here. Had very good score on bread. It ranked number 3 on carrot. Didn't do as great on cheese. It dropped down to 15. So that's middle bottom of the pack there. It did very well on potato, and it did not so great on tomato. And this is one of the things that was so interesting to me. I expected to see that the ranks would kind of be straight bars across this screen. In other words, I thought okay, well, the worst knife is more or less going to be the worst at everything. And the best knife is more or less going to be the best at everything. But in general, that's not what I found, with some exceptions. So here, the Shun Classic Hollow Edge, that's pretty good across the board. That's staying in the top 5 all the way through. The Wusthof Amici, this one was very interesting. So this was, I think, the most expensive knife in the cohort. And you see that it does great on potato. It does great on tomato. It is dead last on carrot. I don't exactly have an explanation for this. And it's possible that if we ran the entire experiment again, I'd get different numbers. But this was all extremely standardized. And these are how the numbers turned out. So I am taking them for what they are. But I think it's very interesting to see a knife go from first place to last place just by switching out the food. And although folks in the community have commented oh yeah, this isn't a surprise. There's a knife that's better for tomatoes and a knife that's better for bread. I don't think anybody expected that the carrot and tomato would occupy worst and last for the same blade. So that is what this is showing. And that was the first big surprise to me. Okay, now I want to take a look at BESS score and how that predicts food cutting performance. Why? Because when we talk about sharpness, sometimes we mean 2 different and specific things. The first thing is keenness. In other words, how perfect is the apex of your cutting edge? If you were to look under a scanning electron microscope, would it come to a perfect single row of atoms? And for all knives, the answer is no. There's a little bit of curving of that apex. And the BESS test, by its own definition, says that it measures a proxy for how perfect that apex is. And it measures it by pressing the knife through a calibrated filament and measuring the amount of force in grams it took for that filament to snap. So that BESS test is all about geometric sharpness or keenness. What I've been measuring with the food cut testing is the other definition of sharpness, which is how much force does it take to cut through the thing you want to cut through, in our case, food. And so we would naturally expect that those 2 measurements ought to, at least mostly, agree. So let's take a look. Here, I've got the BESS scores for each of the blades measured on the y-axis, and then the average of the food cutting metric of interest measured along the x-axis. So to start off, we're just looking at tomatoes, and we can see this linear regression line is pointed the direction we would expect. The sharper the knife, according to the BESS score, the lower the amount of force, or the lower the metric value for food cutting. In the case of tomatoes, we're talking about peak force. So being down here means a lower peak force. Being out here means a higher peak force. And generally, data are pointed the right direction. Up and to the right is what we expect for this relationship. But you can see that our R squared value is only 0.23, which is not very strong. And that is evidenced by sort of how scattered out all the stuff was. If we had a perfect correlation, all of these dots would be along exactly the same line, but they are kind of spread out. Again, we're measuring here the height of this peak. How much force did we apply before we broke through the skin? And you would think that that would really correlate very strongly to how perfect your apex is, but that correlation just is not that great. Let's switch over and look at potatoes. Here, surprisingly, we actually get a better correlation than we did for tomatoes. Here, our R squared value is up to 0.44. And of course, you can see the dots are much closer to that linear regression line. This is interesting because for potato, we measure the average force. So if we come take a look in here, there's not this super important cut initiation thing where we're dropping off. No, the knife is pretty much able to slide right into the potato. If we take a look at cheese, well, cheese is one where I sort of expect there would be no correlation between BESS and food cutting, because cutting cheese doesn't really require a super sharp apex. It's really just about getting the cheese out of the way of the blade. You can, if we really wanted to cut cheese as easily as possible, we'd use like an ultra thin piece of piano wire, and that would glide through the cheese because it has the least amount of cheese to move. So this one actually does match expectations, which is that we shouldn't see that much of a correlation. Carrot is a mess. This is all over the place, basically no predictive power between BESS and carrot, and moderate, a little bit of predicted power between bread and BESS score. The interesting thing happens when these start to fall off at the right hand of this graph, which is we finally sort of cut through, and this doesn't happen in all cases, but we've cut through the bread, and now our force diminishes, but that usually happened at the very end of the cut just because there wasn't that much slicing motion and the knives didn't make their way through. So first interesting thing is that the place where I expected to see the biggest association, we're not really seeing it. So like I mentioned for cheese, maybe this post-bevel thickness has more to do with it. So let's take a look at that. So now we've swapped out BESS score for post-bevel thickness, or thickness behind the edge, in millimeters. And if we look at cheese, our R squared is 0. There is literally no relationship between how much force it takes to slice through cheese and that post-bevel thickness. Carrot, again, R squared 0.03. There's basically nothing there. Bread, also very uninteresting. Potato, 0. And tomato, nothing. So our post-bevel thickness tells us exactly nothing about how sharp the knife is as measured by the effort it took to cut through these foods, at least the way I set up and ran the test. I think that's very interesting. Let's now take a look at the spine thickness. So this is just measured along the top of the knife, and the spine gives us more or less the angle of the primary grind of the knife. In other words, what does the shape of the wedge look like? And for tomato, not a very strong correlation. For potato, it's nothing. For cheese, it's nothing. For carrot, it's nothing. For bread, it is nothing. So again, very surprising. This is the place where I expected to find a relationship between how much cheese were we pushing out of the way based on the shape of our wedge, and how much force did it take to do that. So why on earth wouldn't these two things correlate? Well, I have two possible explanations for where this comes from. The first is that actually the wedge shape does make some difference, but maybe there wasn't enough cheese to see that show up. But explanation number two, is that most of the force that the blade experienced was from the friction of trying to wedge the blade through the cheese. Different blades have different coefficients of friction based on their finishes, based on coatings of the steel, based on the surface roughness. But I believe that that is the force that's dominated our cheese results in particular. And I think some follow-up testing would make that really interesting. Okay, so what does correlate with our BESS scores if it's not our food cutting scores? Well, one thing that a bunch of people expect to correlate will be edge angle. So the narrower your edge angle, the less material you're trying to push through that BESS filament, and the lower a score you should get. So if we take a look at the edge angle, the secondary bevel angle, and BESS scores, again, things are generally pointed in the right direction, but this is a very weak correlation again, which is not totally surprising. If you've ever watched the BESS test under super high magnification, under a microscope, the thickness of that filament is a lot shorter than the height of your secondary bevel in most cases. So it really is just the first part of the apex that's doing the cutting, not the whole thing. All right, so that was not predictive. But what about the edge angle versus food cutting? Maybe the apex is a little rounded, but certainly having narrower or more acute edge angle is going to give you better food cutting than having a wider or more obtuse edge angle. Taken to the extreme, right? Having a sort of a very scalpel-shaped thing ought to cut better than trying to use a log-splitting wedge in there. So we'll take a look again. This is edge angle combined, and here is the average of our food cutting metric. For cheese, correlation is 0. For potato, it's 0. For tomato, 0.03. So this is sort of hope and a prayer that that's actually a relationship there, but it's not representative statistically. Same with carrot and same with bread. So that secondary bevel angle also does not predict sharpness as measured by how much force did it take to cut through these foods. Let's take a look at some data that has nothing to do with food cutting at all and see if the world starts to make a little more of the sense that we would expect. So let's take a look here at CATRA edge retention versus edge angle. This is a thing, if you read, for example, the knife engineering book that Dr. Larry Thomas wrote, there is a relationship in the measurements that he took for edge angle and CATRA. And as we would expect and hope, there was a relationship here, real world, from the measurements that we took. Here on the y-axis, we have the total cards cut across the entire CATRA test. Again, CATRA it's a standardized process for measuring edge retention and or durability by putting the knife in a specialized machine and cutting through a set of calibrated paper cards that are impregnated with an abrasive to do kind of an accelerated wear away at that cutting edge. At the end of the test, you can add up the total cards that were cut, and that's the value that we're looking at here. And a finer edge angle in general is supposed to be able to cut more cards. Even though that apex is going to wear away, you still end up having less knife pushing its way through the cards with an acute angle than you do with an obtuse angle. And that's the relationship that we see here. We can also ask, though, are CATRA and BESS predictive of one another? And the answer there is a little different. Here, we do see that things are pointing the direction that we would expect, but it's not a very close or tight correlation. Rather than looking at total cards cut, because as I mentioned, the knife is going to blunt basically on that first card. I'm only looking at cut number 1. How deep, how many cards were cut in the very first slice? And this first slice was using the factory edge, same edge that was measured on BESS. So does a great BESS score give you great first card cutting? And yes, directionally, but no, not a very strong statistical relationship at all. And I think that is particularly interesting. Another part of the reason the data are more spread here is that we varied more than just the edge angle in these tests. These were 21 different knives made of almost 21 different knife steels at different hardnesses with different heat treatments, with different edge angles applied and different sharpnesses applied by sharpening. So, of course, the data are going to be a little more spread out than if you used exactly the same steel treated in the exact same way, and the only thing that you varied was the edge angle. That was done intentionally as part of QKP because you buy whole knives. You don't get to pick and choose a la carte these facets of a knife's design. But that does contribute to why we don't see a tighter correlation in the places where we expect or know one to exist. Going back to our rankings, I just want to emphasize that even though the rank, sort of the ordered list of who did best in aggregate for food cutting, is the thing that attracts most people's attention, I actually think it's among the least interesting data in the Quantified Knife Project in total. Again, this is not meant to be a competition or to say you should buy the knife that has the lowest blended food cutting rank. I think it's interesting to see results that challenge some conventional wisdom or the sort of group general understanding of what contributes to sharpness, and to see our two definitions of sharpness, one as something like BESS score or apex perfection, and the other as how much force does it take to cut through food. To see those two things not really align as tightly as we would maybe expect, I think that's interesting. And in a lot of ways, the Quantified Knife Project has basically generated more questions than answers. I also think that's a really great outcome here. If you have more questions, you are so welcome to download the data. The Power BI app is free for desktop use. It's Windows only, unfortunately. So if you're Mac or Linux, I'm sorry about that, out of my control. But you can also run your own analysis however you want. The whole point of this was to put the data back in the hands of the community. Thanks for sticking with me on the nerdiest and deepest dive we've done to date on all this data. I hope you got something useful from it. If you have, or if you haven't, please leave me feedback in the comments here. Until then, thanks for watching and happy cooking.